Hello again everyone. So today we're going to look at topic 2.1, which is thermochemistry. You will have done quite a bit of the ideas at the start of this topic in GCSE, so I'm going to kind of integrate it into the A-level stuff and kind of assume you know some of it, but I will try my best to explain it where I think it's a bit easier to forget that stuff. So we got two reactions that I'm going to use to explain it. We've got burning methane, CH4, in oxygen, so it's a combustion reaction which is making carbon dioxide and water. And then we've got, in the second reaction, we got ethanol reacting to make ethene and water. So if we classify these two reactions, this is a combustion reaction. When this reaction happens, things surrounding the chemicals tend to get hotter. This is the opposite thing, so when this reaction happens, things will tend to get colder. So reactions where the things surrounding the chemicals get hotter are called exothermic reactions. And reactions where the things surrounding the chemicals get colder are called endothermic reactions. So why are they called exothermic reactions? Well, in an exothermic reaction, what's happening is the chemicals are losing energy, and because they are losing energy, so exiting, thermal energy is exiting the chemicals, because they're losing that energy, the surroundings, so the thermometer that's by the chemicals, the container, the air will all get hotter because there's energy exiting. And then in an endothermic reaction, energy is entering, so thermal energy is entering the chemicals, so En for entering. Because energy is entering the chemicals, it's being lost from the surroundings, and so the thermometer is losing energy, the container is losing energy, and the air is losing energy, and so things get colder. Now you've represented these before as energy profiles, so I'm just quickly going to sketch one to remind you. So exothermic reaction, we've got my reactants, so CH4 and oxygen, and they're losing energy. So by the time the reaction's finished and made the products, they will have lost energy, like that over there. I think I need to balance this equation, don't I? 2 and 2. So the products have now lost energy compared to how much energy the reactants had before as the reaction went on. In order to get the reaction working, you'd need to provide some activation energy. So this gap here is the activation energy, and this gap here is the energy change, which is given the symbol delta H. And delta H, because the products have less energy than the reactants, delta H would be negative in this scenario. Over on the other side, we've got the opposite case. So this is how much energy the reactants have, and by the time we get to the products have more energy. So here's the CH2, CH2 and H2O, and over this side is the alcohol reactant, which looks like this. Again, activation energy. So this gap here from the reactants to the top is the activation energy, and this gap here is delta H. And delta H is going to be positive in this scenario. So overall, we've got two different types of reactions. We've got reactions where they release energy to the surroundings, so the chemicals are releasing energy to the surroundings, and then we've got reactions where they take in energy from the surroundings, so the surroundings are actually losing energy in this case, but the chemicals are gaining energy. Now if we dig a little bit deeper into what's going on in these reactions, we can draw the reactions to look a little bit like this. So now we're showing the bonds inside the reactants and the bonds inside the products. In order to get this reaction to work, what I need to do in maybe a little bit more detail is break these bonds, so these bonds in the reactants, and then I need to make all of these new bonds. So we can use that then to work out delta H, so that energy gap there. So delta H is the bond breaking energy minus the bond making energy. So if we can work out how much energy we need to break all the bonds over here and how much energy is released when we make all the bonds over here, we will find out what delta H is. We can show that on our energy profile. So this gap here, same as the activation energy, is the bond breaking energy, and this gap coming down here is our bond making energy. So I jump up that much to break all the bonds, and then that much energy gets released when I make the bonds, and the difference between those two gives me delta H, which should come out as negative. Now, if you're asked a question about working out delta H, then they'll give you the bond energies to allow you to calculate it. So let me just find one where they've given the bond energies for this. So I just found it on a paper, but I've written it down. These are the energies for the different bonds that we've got over here. So if I want to work out delta H, I need to work out the total energy required to break all the bonds over here. So 4 CHs are being broken, so 4 lots of 413, and 2 oxygen to oxygen double bonds, which would be 498. So 2 lots of 498. So if I add that up on a calculator, gives me 2,648 kilojoules. So the amount of energy to get up to there is 2,648 kilojoules. If I get bond making energy, so bond making energy, I'm making a carbon oxygen double bond and another carbon oxygen double bond, so 2 lots of 805, and then I'm making 1, 2, 3, 4 OH bonds, so 4 lots of 464. So let's put that in a calculator. Gives me 3,466 kilojoules. So that's the energy that gets released when I make these bonds, when I make the bonds in the products. So delta H is going to be 2,648 minus 3,466, which gives you minus 818 kilojoules. So delta H, this energy gap there, is minus 818 kilojoules. You can think about your answer as negative, so that makes sense because it should be negative for this answer. If it came out positive, I'd be questioning my maths skills for that question. So you have the exact same principles that apply for a endothermic reaction. These chemicals are made, have bonds that hold them together, so we'll draw a displayed formula for them. It's reacting to make ethene. Ethene looks like that, and H2O, HOH. So I've got to break all these bonds, and then I've got to make all the bonds over here. In this scenario, bond breaking is that gap, and bond making is this gap over here. So let me just quickly calculate that for you. Okay, so there's the calculations just to save a bit of time. Those are the bond energies. Delta H is bond breaking minus bond making. Bond breaking energy there, so that's the energy required to break all the bonds here, and bond making energy over this side, that's the energy released when we make the bonds. Breaking minus making gives me plus 42, and again that makes sense because I know that this reaction is endothermic, so that plus value makes sense. And the energy change is plus 42. Now you get some questions which ask you to use ideas about bond breaking and bond making to explain why a reaction is endothermic, or use ideas about bond breaking and bond making to explain why a reaction might be exothermic. So if we look at exothermic to begin with, you can see in an exothermic reaction, the energy required to break the bonds is that much there, but the energy that we get released when we make new bonds is much bigger than the energy required to break the bonds. So a reaction is exothermic when the energy required to break the bonds in the reactants is less than the energy released when we make the new bonds in the products. If we go over to endothermic, there's the energy required to break the bonds, there's the energy released when we make the new bonds. In this scenario, the energy required to break all of the bonds in the reactants is greater than the energy that gets released when we make the new bonds in the products. So if you're asked to explain it in terms of bond breaking and bond making, those are your explanations. Another thing to note is the fact that bond energies, so here's a set of bond energies and there's another set, bond energies are always positive. That's because it always requires energy in order to break a bond. So a bond is holding two atoms together, you need energy in order to break those bonds there. And then the final thing that I want to mention in this section is the idea of a standard energy change or enthalpy change. So you get this symbol, which I haven't drawn very well there, so delta H, and then a circle with a line through it. There's a superscript, means a standard energy change or standard enthalpy change. Probably better to use the term standard enthalpy change for this. So standard enthalpy change. Which would represent that gap there or that gap there, done under standard conditions. So you should remember standard conditions are 298 Kelvin, 100 kilopascals of pressure, and then if you've got any solutions, they need to be 1 molar concentrations. So standard enthalpy change is the enthalpy change that takes place in a particular reaction performed under these standard conditions. Or you can think about it, the standard enthalpy change is the amount of heat energy that is absorbed or evolved in a particular reaction performed under standard conditions.